and multi-component system. So we restricted our analysis with two phases. Okay. So and what the equations for the, so you have first phase and second phase, temperature and pressure, equilibrium, and also Fi of first phase, Fi of second phase. The specifications we have T1 equals to T2, T1 equals to T2, and once you say that if IL TP X bar equals to FIV TP Y bar, this single equation, not single equation, one single representative equation for all the I components would suffice for the main algebraic equation for the vapor equilibrium. So FIL TP X bar equals to FIV TP Y bar, and this is valid for the VL. Is valid for the VL. And that was the starting point. That was the starting point. So we are talking about the vapor liquid equilibrium at low pressure. So we'll do such a way. Vapor liquid equilibrium will go for the low pressure, and then some approximation, maybe vapor phase will be a low pressure, the liquid phase the moderate pressure, or the moderate pressure calculation, and then we'll go for the high pressure. So we'll have situations like low pressure. We have something like moderate pressure, and we can have high pressure. This high pressure is having generalized calculation. Okay, so all the places will be talking about solution of FIL equals to FIV. All the places will be talking about solution of FIL equals to FIV. Okay, so low pressure, moderate pressure, high pressure. All the places will be talking about this. And so what actually happens? This low pressure will have some special approximation, which is Rao's law. Moderate pressure will have approximation. We have different activity coefficient model. So activity coefficient you might have heard about, right? Activity coefficients. Okay. Those models will come from moderate pressure calculation, and high pressure is basically based on equation of state. US based approach. Most generalized. US based approach will be useful for all cases, low pressure to high pressure. But low pressure, moderate pressure, if you use Rao's activity coefficient, the calculation is simple. The calculation is simple. You don't have to, because US based approach, you need to solve by iterative methods. It is sometimes expensive and it's not worth it for the low pressure, moderate pressure. But for high pressure, when all those approximations will fail, you have to go by iterative method. And that is most generalized. So equation of state-based approach, which will be solving this FI equals to FIV, and that is more generalized. Okay, so yesterday we were talking about the Rao's law. So FIL equals to FIV. Rao's law, where we have FIL equals to FIV. And at low pressure. At low pressure. So this is FIL for the liquid phase at the low pressure. We go by Lewis-Randall rule, and for the vapor phase we go by the method by partial pressure. You know, FIV. So which will be because we know that FIV equals to P into YI into exponential mu y minus mu y IgM by RT. Am I correct? Yes. And then it will actually, this mu y minus mu IgM will actually behave like IgM. So mixture behave like IgM. So the exponential, that term is equal to 0, so 3% equals to 1, and FIV equals to Py. So this will be approximated as Py. Fi of L, component of fugacity of liquid phase. Liquid phase of fugacity, we have the least standard rule, which is Xi, Fi star. We talked about yesterday. Xi is the mole fraction of the component in the liquid phase. X standard. Fi is the pure component fugacity of ion component. Pure component fugacity. And the pure component of fugacity, when talk about, we have done it earlier. For the pure component fugacity, what we actually, I just want to have very fast recap how to do it, liquid phase fugacity calculation. I think by all of you understood what is saturation pressure, Fi star. So evaluation of Fi star. Evaluation of Fi star at low pressure. If you talk about evaluation of Fi star, you just remind, this is your PV diagram. This is your PV diagram. This is your low pressure zone. This is I, this is I prime. Right? The same thing I am doing. So, the fugacity for the pure substance is again defined as F by P exponential 1 by RT mu minus mu Ig. You can say Pp, and also you can write this as F equals to P exponential. This entire thing you can write 1 by RT and mu minus mu Ig. The formula is mu minus Ig integral 0 to P. What is the formula? Quick. What is the formula? Only one person? Yes. B minus RT by P prime. B minus RT by P prime. Okay. So you are in this. So when I talk about Fi star, this Fi star is coming here. F star. This I star, I prime is something, some point. F star is here. Pure component liquid phase fugacity. F star is here. So what do you actually do? So it is nothing but FL. So RT ln FL by P, which is P equals to 0 to PID, which is Vg minus RT by P prime dP prime plus PID Pi prime P VL minus RT by P prime dP prime. So my P tends to 0 is here. So I will be coming to, so I and I prime will be the same line. Okay, saturation pressure. So P tends to Pi, or maybe I will be here, I prime will be here, whatever. So Vg minus RT by P prime and then Pi to Pi prime. The same thing I have done in the class. I don't have to explain it. And then this actually is what? This is nothing but RT ln FB by PR. FB by PR. The pressure is PR. Okay. So overall we will get, we have already got some nice formula here. Which is FL by PI prime, PI prime by PI, which is FB by PI, which is exponential 1 by RT PIT PI by P VL dP. That's what we have done earlier. This is a pointing pressure correction. And if Pi equals to Psat, if Pi equals to Psat and Pi not Pi prime not equal to Psat, okay? So I will be here and this I prime some other point, liquid phase, okay? FL. What actually happens? This is, it will be FL by FB sat exponential of 1 by RT, which is P sat by Pi prime D VL dP prime. The question is the very low pressure. The low pressure, this difference is very small. Okay, so this goes to 1. So if FL equals to FB sat. Okay, and FB sat is a vapor phase. Low pressure from this expression, vapor phase, it will be FB equals to P. FB sat equals to P sat. FB equals to P means FB sat equals to P sat. So at low pressure, FL equals to P sat. That means Fi star, which is equals to Pi sat. That's why I told you yesterday. Right? All this entire thing I have done earlier in the class. So that's the way you have to estimate the See, vapor phase is very straightforward. Fugacity. Up to this vapor phase, then after liquid phase. Vapor phase is very straightforward because liquid phase you have to add the vapor phase and then the liquid phase, and that's how the Poynting pressure correction comes. Okay, the Poynting pressure correction will not come for the vapor phase, so liquid phase it will come. And if it is low pressure, then it is possible to prove that the pure component fugacity Fi star equals to Pi sat. Okay, so with that, so once it is fixed, what you get to from the vapor liquid equilibrium at low pressure. So for the low pressure, the vapor liquid, so we have FIL equals to FIB, which is Xi Fi star, which is Pyi, Xi Pi sat equals to partial pressure of ith component, and that is the Raoult's law. That's the Raoult's law. That's what we have derived yesterday. Okay. So Raoult's law. Earlier we didn't know anything. Now we know that it is nothing but equality of fugacity in liquid phase and vapor phase. It is nothing but equality of fugacity in the liquid phase and vapor phase. Problem set 4, number 1 problem. Problem set 4, first problem. Benzene and toluene form an ideal solution. The vapor pressures of benzene and toluene are adequately represented by the Antoine equation. Which is log 10 P A minus B by T plus, where P is in torque, and T is in degree centigrade. P is in torque. Torque is millimeter of mercury. Torque means millimeter of mercury. The question is prepare a PXY diagram at 95 degrees centigrade. The second question is prepare a, so you don't have assignments with you? Okay, I just circulate the assignment. You don't care for taking it, so that's it. But I think my friends have 3 to 4 people whom I don't think you have also. So you don't have that. Okay. But you two have only one?
No, I have.
Okay, that's what. So only 3-4 guys actually having the assignment copy, that's it. So I don't have any problem. So they can actually respond. I don't care. Yeah. Okay, because you also don't care for my lecture. Just you may think just one. That's okay, no problem. Prepare a PXY diagram 95 degrees centigrade and prepare a TXY diagram at 101.325 kilopascal, right? Which is 7 kilopascal in 760 torque pressure. And Antoine constants are given, right, in the table format? Yes. It is A, B, C. It is the Antoine constants, A, B, and C. So let's start the PXY diagram. Let's start the PXY diagram. So for PXY diagram, we do slight derivation from the Raoult's law. We have YIP equals to XIPI sat. Okay. That means Y1P X1 P1 sat, Y2P equals to X2 P2 sat. If you add them up, you will get P equals to X1 P1 sat plus X2 P2 sat. And one can, and X1 plus X2 equals to 1. So you can write, which is P1 sat plus P2 sat, P1 sat minus P2 sat X1. Am I correct? Yes. So one can actually have diagram P versus X1. How the diagram will look like? This is varying from 0 to 1. How the diagram will look like? How? Curve 1. Curve. Is it curve? Is it curve? Is it curve? See, P1 sat, P2 sat, we look at the function of temperature. First question, temperature is constant. So P1 sat, P2 sat will not change. So how it will be? It is y equals to x plus b. This is the source flow. So the intercept is P2 sat. So this is P2 sat. This is P2 sat. Okay, so this space x1 equals to 1, so it is P1 sat. From this equation, everything is coming from the equation. If you want to have the partial pressure, which is, this is y1p. y1p is what? x1 P1 sat, that is passing through origin. Slope is P1 sat. And it is converging there because at x1 equals to P1 sat. Similarly, y2p will be how the y2p curve will be? How the y2p curve? How the y2p curve will be?
It should be starting from 1.
1.
It will be going to B.
This type?
Yes, sir.
y2p. Okay. So now let us solve the first problem. So I need to have the diagram, pxy diagram. Pxy diagram. So this is a P2 sat, P versus x. So we have now pxy diagram. So what diagram actually I am expecting? We have P dot pressure. We have x1, y1. P versus x1, P versus y1. Here it is liquid plus vapor mixture. This kind of diagram you might have seen quite often. Okay, you really know how to derive it. This is the consequence of the equality of fugacity at low pressure. At high pressure, we have to see how to do it. High pressure, this diagram will be changed. So all the books they have talked about this diagram is based on the Gauss at low pressure. At high pressure, this diagram we have to see how to draw it. Okay, how to draw this diagram? How to get this diagram? So we have to have pxy diagram. Equation is y1 equals to x1 P1 sat by P. Equation number A. So the steps, choose x1 0. Number 2, calculate P. Number 3, obtain y1. So this equation I am saying equation number A, this I am saying equation number B. So obtain, calculate P from equation A, and this is from equation number B. Okay. So let's start. I think you have your calculator handy. Have the calculator handy. Then go back home, put the MATLAB or have the graph paper, get the nice curve. That I want to see on Friday. The graph, the curves. x1, y1, P plot pressure. I am giving the values 0, 0.1, 0.2, 0.4, 0.6, 0.8, 1. Give me y quickly, y1. If x1 equals to 0, what is y1? P plot pressure. P from equation number 8. x1 equal to 0, so P equals to P2 sat. What is P2 sat from Antoine equation? P2 sat from Antoine equation. In Antoine equation, you have ABC. Second component, put the value of ABC. Temperature is 95 degrees centigrade. In Antoine equation, temperature is in what? In centigrade or degree Kelvin? Degree centigrade. That's it. Your job is done. Temperature in degree centigrade. Your job is done. Temperature is in degree centigrade. So what is the, how much is the value? X1 0. What is the value of Y1? So value of Y1 equals to 0 from this equation. So the equation number P, Y1 is giving 0, but P will not be 0. P is something. What is P? Quickly calculate. You have the memory function ready because next you have to calculate for point 1. You need to have memory function ready. You need to have memory function ready. How much is P2 set? Or P? 477 torr. 477 torr. Next point 1. Quick. If Y1 is X1 is 0.1, X1 is 0.1 means 0.1 P1 set by P. P is how much? You know that. P is 760 torr. P1 set you have to calculate. So make P1 set, P2 set handy. Keep it handy. P1 set, P2 set, you keep it handy. Use it. Use the memory function. Give me the solution. At least 0.1, 0.2. Rest of things you can do at home. How much is Y1 for 0.1? What? Pardon? 0.0267. 0.06. No. Y1. Y1, how much it is coming? Simple calculation I am asking for. I am asking for simple calculation. Any Y1 values from anybody? First calculate P1 set. Your P is there with you. X1 is 0.1. It's very simple. Antoine equation is given. I don't think any problem is there to calculate. It's very, very straightforward. How much is Y1? Antoine equation is given. How much is Y1? 0.15. I am getting second answer 0.15. 0.15? Yes. 0.15. Third answer or same answer 0.15? Is that correct? Rahul? So simple calculation taking so much of time, huh? I am really surprised. I am really surprised. Which is just like BTech level calculation, it's not like master's level, what I am teaching. If you want me to do in the board, that will be real disaster. If you want me to board this calculation, that is not correct. Please check your calculation, 0.15 is not correct. Of course not. Otherwise I would have actually finished the call and go for the or gone for the second one. 0.15 is not correct. 0.215. So I had to shout so much to get the answer. I am really, really surprised. And what's the P torr? 546.92. 0.2. Move to 0.2 first. You have everything ready. P1 set, P2 set. P1 set, P2 set, make it handy. 0.2 how much? It should not be having so much of time. Quick, it should be quick. Memory function. 0.2 how much? Your P1 set, P2 set are ready. P is 760 torr. 0.3814. What is P torr? 616. Okay, Point 4 is how much? Point 4. Calculate P and then use that equation B. First equation A, then second equation B. Calculate P, put the P here and get Y1. For calculating P, it is very straightforward because now you have P1 sat, P2 sat. You keep P1 sat minus P2 sat handy. That is better. Then just use memory function. Make it handy. P1 sat minus P2 sat. Pardon? 16218. And then 756.68. So you can do all those and then finally you get here 1 and 1176.2. So if you have this all the things and just put it here, you get P versus X1 and P versus Y1 from this 3 column. Okay? And you get the TXY diagram, what you have seen in the book. So now you can see that these books, the calculations are done in Trevor's book. You might not have imagined that this much of procedure is required to have this PXY diagram. And what it requires Depal liquid equilibrium, fugacity quality, from there Gauss law, and then Antoine equation. Without Antoine equation, you cannot get this curve. Next, we will go for the TXY diagram. Second part. So the TXY diagram, your pressure of the total pressure is fixed, right? Total pressure is fixed to 760 torque. We have the Antoine equation. So next we will be going for the TXY diagram. Next we will be going for TXY diagram. We have log 10 T sat, which is A minus B by T sat plus C, and then T sat you can calculate as B by A minus log T sat to the base 10 minus C. Y1 P equals to X1 P1 sat, Y2 P, then we know X2 P2 sat. Okay. So you have to calculate. So choose temperature. First step. So here temperature is not fixed. So temperature we choosing from say T. 80 you can actually select 80 to 110, 120, whatever. Number 2 is calculate P1 sat, P2 sat. Calculate P1 sat, P2 sat based on Antoine equation. Number 3, calculate X1 from this following equation. P equals to P2 sat plus P1 sat minus P2 sat X1, and X1 is P minus P2 sat by P1 sat minus P2 sat. Calculate Y1. Okay, so Py1 equals to X1 P1 sat. P1 sat is obtained from the first second step. P is known, the pressure is fixed here, so X1 P1 sat by P, right? So 4 steps calculation. So I give you the temperatures. Degree centigrade. I am saying 80.1 initial calculation. P1 sat dot P2 sat dot X1 Y1. Quick. 80.1. Why I am taking 80.1? Because if you put x1 equals to 0, what actually happened? I will say the basis of the 80.1 calculation. For x2 equals to 0 and x1 equals to 1, p equals to p1. Am I correct? P equals to p2 sat plus p1 sat minus p2 sat into x1. If x1 equals to 0, p equals to p1, right? So T1 sat, which is B by A minus log 10P minus C. So how much is T1 sat? Can you tell me T1 sat how much? Then x1 equals to 1 and x1 equals to 1. At x1, so your limit should be from x1 equals to 1 to 0. So you need to have a lower limit and upper limit of temperature. P equals to x1 equals to 1, so this will get cancelled, so P equals to P1 sat. With that you know that temperature has to be obtained from here. How much is temperature? 80.1. So if I say x1 equals to 0, y1 equals to 1, what will happen? We don't know. That's why we just question mark. x1 equals to 0. You have to find out from that. x1 equals to 0, temperature is 0, so you can say temperature range. I want a temperature range here. So it will be P2 sat, right? If you put x1 equal to 0, what will happen? P equals to P2 sat, right? What is then T sat? T sat you obtain from this equation. For second component, how much is T sat? If you have the ABC end-to-end equations, end-to-end numbers, nobody is doing calculation. I think only 2-3 guys. Many of the guys will be having, won't be having assignment also. 110. How much? 110. Is that correct answer? How much is the correct answer? How much is the correct answer? 110.61. So you got that lower limit and upper limit. So now calculate P1 sat and P2 sat. Already you have that P1 sat, P2 sat calculation at that particular temperature. P1 sat, P2 sat. How much is P1 sat and P2 sat at particular temperature? P1 sat, P2 sat. 80.1. How much is P1 sat? How much? 760 top pressure. P2 sat? Pardon? P2 sat? 290. How are you getting P2 sat 290? 0, yes. It is 0. Rahul, I think something is going wrong for you today. It's simple. I am doing BTech stuff here, not MTech anymore. Y1 is 0. Y1 is what? X1 P1 sat by P. P1 sat and P are same. So it is 1. Next is, so you can actually have increment. So see, now you have seen the limit 80 to 110. You cannot find limit 85, 90, 95, 100, 100. That's the way you can actually give the fit MATLAB, and MATLAB will plot that TXY diagram. Next is 85. 85 P on SAT. How much it will be? 85. What is the P on SAT? 85 P on SAT. Antoine equation is there. Now it's pretty straightforward. We have Antoine equation. Log 10 P to SAT, log 10 P on SAT, A minus B by T plus C. A, B, C are there? Yes. Pardon?
881.
881. That one is very lazy to tell all digits. Okay, P to SAT. P to SAT. P to SAT is how much? $345.22. What is x1? We don't know the x1. We have to calculate x1, which is P minus some formula I have given. Yes, by P1 SAT minus P2 SAT. If you use that formula, you can calculate. Because by now P1 SAT, P2 SATs are known. X1 is how much? X1 is how much? Pardon? 0.7734. And Y1? Y1 is how much? 0.8971. So like that you can actually do that your card, and you can show next class. I want to see the MATLAB or draft paper plot of TXY diagram. So maybe Rahul or Devan or somebody can show it to me. And the diagram is well known. The diagram I can draw here. We have seen in the mass transfer book. This diagram you might have seen. Okay, 3 degrees centigrade, which is x1 or y1. This is T versus x1, and this is T versus y1, and this is called dew point curve, and this one is called bubble point curve. I think you have seen all those things. And this is a liquid plus vapor regime. We have seen dew point curve and bubble point curve. So what we have done in the undergraduate level, this is the line, and if you start reducing the temperature, you get the first drop of liquid, the dew point. Then you go here in this line, you get vapor liquid mixture. You get here the last drop of vapor will go to the region. So that's why it is called dew point and bubble point. Similarly, if you want to start from here, the first drop of vapor forms bubble. Then you go here, the last drop of liquid will go. So that's the thing, and that entire thing, the entire diagram is based on low pressure. The high pressure, you have to see how the diagram behaves. And from there, aziotropy or all those things will come in mass transfer. I am not going to details. Aziotropy calculation, please refer to Professor Ravi's paper of INDC, which just got published. Okay, so this diagram you will see when you draw the MATLAB curve. So entire degree of freedom calculation phase rule for the vapor liquid equilibrium can be summarized. So VLE at a glance at low pressure, VLE at low pressure, which is F equals to C minus 5 plus 2, and you have got two components, two phases. So 2 minus 2 get cancelled, we have 2 degrees of freedom. So that 2 degrees of freedom means we have to give 2 things at a time to solve the problem. So there are a lot of combinations, and if you look at the unknowns, we have liquid phase unknown, we have vapor phase unknown. Okay, I won't generally write liquid and vapor because I am saying x1 and y1. There are 6, and unknown equations are TL equals to PV, PL equals to PV, and we have Fi L equals to F1, L equals to F1B, F2 equals to F2B. So there are 4 equations, and that's the way we can justify the degree of freedom 2. So since degree of freedom is 2, so that means 2 variables have to be given to get in solution. So given, and to calculate, if T x bar given, then you have to calculate P y bar. Right? T x bar given, you have to calculate P y bar. This problem type, which is called as bubble pressure calculation. This kind of problem is called as bubble pressure calculation. T y bar given, you have to calculate T x bar. What will be this problem? What will be this kind of problem? First one is bubble pressure calculation. This one is dew pressure calculation. This kind of problem is known as dew pressure calculation. We can give Tx bar, calculate Ty bar. What will be this kind of problem? What will be this kind of problem? Bubble point temperature calculation. Bubble temperature calculation. Bubble temperature calculation. Next we have Py bar. Sorry. Yes, Py bar. We have Tx bar. We have dew temperature calculation. Okay, so next we will be starting the bubble and dew point calculation. So bubble point calculation is pretty straightforward. We will see here how the iterative process will actually work. We need to have iterative process for bubble point and dew point calculation. So before finishing that, your class today, I'll just summarize the bubble point and dew point calculations, how the algorithm will look like. So we have the components. So P equals to generally x1 P1 sat plus x2 P2 sat, and we have xn Pn sat. We have n number of components from Rao's, right? From Rao's we can prove it. y1 P equals to x1 P1 sat, y2 P, and if you sum it up, you get Dalton's law, partial pressure factor P is nothing but summation of x sat Pi sat, right? So this which we call as xi Pi sat T bubble point. The total pressure is given by this. And so what actually, so given is Tx bar, we have to calculate y bar. How to calculate y bar? y1 equals to x1 P1 sat by P. x1 is given, temperature is given. If temperature is given, Anton equation will give you P1 sat. Temperature is given, Anton equation will give P1 sat. P is obtained, so you can get y1. This calculation is very straightforward. Bubble temperature calculation is very straightforward. What will happen for the dew point calculation? For the dew point calculation, given is Ty bar or Py bar, then you have to calculate xi, right? Dew point, y1 is given, T is given or P is given. So you have to calculate x1, which is y1 P by P1 sat, or Rao's law, which is the function of dew point, TdP. The temperature is very important. And remember that summation xi equals to 1. If summation xi equals to 1, we can write as y1p by P1 sat TdP plus y2p by P2 sat TdP equals to 1. So P is 1 by by P1 set plus Y2 by P2 set and so on. If the temperature is unknown, the problem. That means we do some iteration. Temperature is unknown. That's a problem. That means the problem case will be Ty bar and Tx bar. If temperature is unknown, what actually happen? You cannot get the pressure just like that. If temperature is known, you can get the pressure easily from Anton equation. If temperature is unknown, if you don't get the pressure, big problem. So do some iteration. So that's the second problem. So I will discuss the second problem in the next class. Analysis.